Okay, have you ever stopped to think about how an AI really understands language? I mean, without a dictionary or a grammar teacher, how does it get what we're saying? Well, we're going to pull back the curtain on that because the answer is one of the most elegant and powerful ideas in all of artificial intelligence.
It really all boils down to a question like this. How on earth can a machine figure out the connection between king and queen? It feels like there has to be some kind of magic involved, right? But it's not magic at all. The answer is actually surprisingly simple.
And here it is. This is the whole secret, summed up in one sentence by the linguist J.R. Firth. You shall know a word by the company it keeps. It's not about defining the word itself. It's about looking at the words around it. It's all about context.
What's so wild is that this huge idea didn't come from computer scientists trying to build some futuristic AI. Nope. It started way back with linguists who were just trying to figure out the fundamentals of how we, as humans, use language.
This is what they called it, the distributional hypothesis. And the logic is just beautiful. Basically, if two different words keep showing up in the same kinds of sentences, surrounded by the same kinds of neighbors, well, they probably have similar meanings. Meaning isn't some fixed thing inside the word. It's shaped by the context it lives in.
And you can see how this idea grew up over time. It starts out as this cool linguistic theory in the 50s. Then, as computers get more powerful, it becomes a real statistical tool in the 90s. But the absolute game changer was in the 2010s with things like Word2Vec. That's when this theory got supercharged and became the engine inside the AI you hear about today, like GPT and BERT.
So, how does this actually work? Let's make it super simple. Imagine an AI reads, I don't know, 1 billion sentences, and it keeps seeing this pattern over and over. The blank is sleeping. What kind of words do you think could pop into that blank space? Right, things like dog, cat, baby, lion. By seeing that all these words fit comfortably in the same linguistic spot, the same neighborhood, the machine doesn't need to be told what a dog or a cat is. It just infers that they're related. They must be part of a similar category of things that are capable of sleeping. Simple as that.
Okay, that all sounds great as a theory, but how do you actually get a computer to understand these neighborhoods? How do you turn this cool linguistic idea into something a machine can actually crunch the numbers on?
The answer is something called word embeddings. This is the trick. We basically turn words into long lists of numbers called vectors. Think of it like giving every single word a coordinate on a giant, complex map of meaning. And on this map, words that keep similar company get placed right next to each other.
And this, right here, is where things get really mind-blowing. Because once words are just numbers, we can start doing math with them. And with simple math, we can uncover these incredibly complex, almost human-like relationships in our own language. Check this out. This is a famous example from the Word2Vec model. We can literally take the number vector for king, subtract the vector for man, and then add the vector for woman. Now, if you do that math, what words vector do you think you'd end up closest to on that map?
You get the vector for queen. Let that sink in for a second. The AI has learned the abstract concepts of gender and royalty just by looking at statistical patterns in text. It's using math to solve an analogy. This isn't just playing word association. It's actually capturing the essence of meaning in numbers.
But you know, language is slippery. That company a word keeps can totally change what it means. And this was a huge problem for those early models.
For example, take a word like bank. Are we talking about a place you deposit money, or are we talking about the side of a river? How can one single coordinate on our map, one static vector, possibly represent two totally different ideas? It can't.
Because if you see a sentence like this, the company, words like deposit and money, are all giant clues pointing you towards a financial meaning. The context makes it crystal clear. But then in this sentence, the company is completely different. Sat and river create a totally separate vibe, pointing to a geographical meaning. The word is the same, but its meaning is completely transformed by its neighbors.
And that's the huge leap forward that models like BERT and GPT made. Instead of having just one fixed address for the word bank, they generate a new, unique vector for it on the fly every single time it appears, based on that specific sentence. So the meaning of bank is no longer static, it's dynamic, it's alive to the context.
So, what does this all mean for us?
Well, this fundamental principle isn't just some dusty old theory anymore. It is the engine that is powering so much of the technology we interact with every single day.
Seriously, when you type something into a search engine, it's not just looking for keywords anymore. It's using this very idea to understand what you actually mean. It's behind better machine translation, those spam filters in your email, sentiment analysis, pretty much any task that needs a real grasp of language.
And this is just the beginning. The next big step is to expand what we even mean by context. For these new multimodal models, the company a word keeps won't just be other words. It's going to be the images, the sounds, and the videos that appear with it, creating a way deeper and richer understanding of meaning.
So if you take one thing away, it's this. Meaning isn't defined, it's learned from context. It's an incredibly simple idea that lets AI map our language into a world of numbers, solve analogies with math, and dynamically understand words in a sentence. This one principle has gotten us this far. So it leaves us with a pretty big question. What happens when an AI's context expands to include everything we see, everything we hear, and everything we say?